In the last video, we took a look at steady state systems and from there discussed how a battery works. Now I'd like to get a little more quantitative about describing the work done by a battery. And so to that end, I'll go back to our friend the Van de Graaff generator, the literal conveyor belt of charge. So here's my conveyor belt, turn around like this. We were picking electrons up off of this plate over here, moving those electrons this way and then putting them onto this plate over here. As a result, as we pull electrons off, this plate becomes positively charged. This plate becomes negatively charged. And we saw that we were forming an electric field between the plates. Like so. And what we realized is that in order for these charges to move at a constant speed, they're feeling an electric force to the left. So that means that the Van de Graaff generator itself has to be exerting a force on them to the right to move them along. And since we're applying a force and going through a distance, this means we're doing work. Now, usually we're not so interested in the actual amount of work done as we are in the work done per unit charge that gets moved. So we define the EMF. Now this is a cursive capital E. There we go there. Just so we know what it is I'm writing, it's not an epsilon. An epsilon would be half the height. So this is a cursive capital E. This gets called the EMF, and it's defined as the work done by the battery. Remember, the Van de Graaff generator here is a battery, but so's a galvanic cell or whatever, over the charge that got moved. So the work done to move some charge divided by the charge. So the units here will again be joules per coulomb, which are volts. Now, this gets called the EMF, and you may be wondering what it stands for, and I'm not going to tell you. This is because it refers to a previously held incorrect model of electricity. And you would do well to not look it up. I'm really not trying to neg you into looking it up or anything like that. You would avoid confusion by not looking it up, at least until well after you're done studying this. The name, no one ever refers to it by what the letters used to stand for. We just say the EMF. There's been a trend in recent years to not even write it in capital letters. But it looks weird because then you just see EMF. But it's not pronounced EMF, it's pronounced EMF. So I know that's a bit cryptic, but that's really the best way to go. So it's just, this is the non-conservative work done by the battery per unit charge. Whereas the potential difference we saw was the change in potential energy per unit charge. So this will go into our energy balancing. So just to get some sense of this, let's just play with some numbers here. Let's say we have a battery that did 0.6 joules of work to transfer or to move 0.05 coulombs of charge from where it electrically wants to be to where it electrically doesn't want to be. let's find the EMF. So in this case, the EMF would be the work done by the battery to move that charge over the charge. So there'll be 0.6 joules over our 0.05 coulombs is 12 volts, which is the voltage of a typical car battery. So that seems like a perfectly reasonable number. So when you look at a battery, what they always rate a battery at is the battery's EMF. We'll find out that will differ somewhat from the actual voltage you would read if you put a meter across it while it's operating. This has to do with the internal resistance of the battery. We'll defer that for now, but the EMF is the terminal voltage when there is no load. When there is a load, you will have a little bit of drop in the voltage if you're discharging, a little bit of gain in the voltage if you're charging the battery. But for now, let's just take everything as ideal physics batteries and say that the voltage across the terminal is the EMF of the battery. Okay, the other thing I alluded to in the previous video was conventional current. But before we get to conventional current, let me just remind you about how we thought about water current. So when we did fluids back in the day, the idea was, say, if I stood next to a river, like so, there would be water flowing down the river. And I could characterize how much water is flowing down the river if, say, I stood by the side of the river here. And count how many liters of water went by every second through this plane here. And that gave us what we called the volumetric flow rate of the river, which was measured in liters per second. We can do something similar with electric current, but we have to be a little more careful. We're going to define what we call the conventional electric current. And I'm going to put the word conventional in parentheses here. This is because if we just say the electric current and we don't specify otherwise, we always mean this conventional current. If we're talking about something more specific, like, for instance, the flow of electrons, and we're interested in the electrons, then we'll talk about the electron current. But the idea is the same. So I can imagine here, this is a wire. I can go ahead and cut a plane through my wire and just stand, just like I was doing with the river. I can stand by this plane and I count how many coulombs of charge pass the plane every second. Now, the thing here, though, is we have to be a little more careful. As we saw with the galvanic cell in the previous video, we can have it, say, where positive ions, for instance, within the chemicals of the cell, could be drifting to the right at the same time that negative ions are drifting to the left. And so we could have both positive and negative species moving at the same time. But the thing is that they will both have the same effect. So let's say that the conventional current is flowing through like this. The symbol for conventional current is a capital I. What we could be having happen is we could be having positive charges flowing this way, or we could be having negative charges flowing the other way. Or even both at once. And if both at once happen, let's say I have a positive charge going to the right and a negative charge going to the left through the plane at the same time, we would count each of them. We would imagine standby every time a positive charge passes to the right or a negative charge passes to the left. Either way, we click our little counter counting the charges until a second passes, and then we read and see how many charges that is. And this is because from the perspective of building up charge on the terminals of the battery, it really doesn't matter if we move positive charges to the right or negative charges to the left. Now, outside of the battery, it will typically be the case that what is flowing will be the electrons. So if I hook up a wire to the terminals of the battery and I wire in a toaster or something like that, we're going to have electrons flowing through all of that. And so as we're going along, you may find yourself kind of cursing out Ben Franklin for a moment here, because you may find yourself being annoyed by the fact that when we say the current is flowing to the right through a wire, we really generally mean that electrons are flowing to the left through a wire. And this is just because Franklin decided way back in the day, in his definition of positive and negative charges were what made the electron negatively charged in his convention. Now, before you get too bent out of shape with good old Ben here, keep in mind, inside a battery, we can have both positive and negative ions flowing at once. And there are electrical systems that are built around species other than electrons. For instance, in the nervous system, we could be talking about the flow of positively charged potassium ions. So in that case, the conventional current points in the same direction as the flow of the charge-carrying species. I guess for myself, I would sooner it be that my doctor is less confused about charged species flow versus conventional current flow than, say, an electrical engineer. Figure the electrical engineer will work it out, but I definitely want to make sure that my doctor doesn't get confused on that point. But that's just me. All right, so with all of that having been said, we can go ahead and define this very similarly to what we did with volumetric flow rate back in the day of fluids. We will define the conventional current to be the amount of charge that flowed past our plane per whatever amount of time we were measuring it in. So as far as our units go, the unit of current is the ampere. English speakers almost always say amp, like so. And 1 ampere, the symbol's capital A, is 1 coulomb per second. Now, we'll get into this when we get into the unit of magnetism some more, but in the SI system, officially the ampere is the base unit and the coulomb is the derived unit. And that has more to do with historic back compatibility than anything. So the official definition of the ampere is based on saying the fundamental quantum of electric charge equal to an exact number, but then the they and they say it's that many amp seconds, where an amp is a coulomb per second. It's a little tedious. Really, the coulomb at this point is the base unit, but for historic reasons, it's the amp. Don't worry about that so much now, but that's something that will rear its ugly head just a little bit when we get to the unit on magnetism. So just to get some sense of how this might work, we can think about, say, a nerve cell that's depolarizing. So when that's happening, charge will get transferred across the cell membrane, which will change the potential difference across that membrane. For a typical nerve cell, the typical amount of charge that will flow will be something on the order of 9 picocoulombs of charge. And the time over which this occurs is usually something like half a millisecond or so. So we can get some idea of what the current is through our membrane, through our cell membrane here. This would be, delta Q over delta T. Now we got to be careful about our units here. 9 picocoulombs. Remember, the pico prefix means 10 to the negative 12, so this will be 9 times 10 to the negative 12 coulombs. Milli means times 10 to the negative 3, so it'll be 0.5 times 10 to the negative 3 seconds. This will give us 1.8 times 10 to the negative 8 amps, or we can write that as 18 nanoamps. So we're not talking a whole lot of current flowing, but there is indeed a current flowing. Alrighty, so with that, we'll go ahead and call it here for the moment, and we'll pick up again looking at resistance. Catch you over there.